Professor Sargent here with you again for another Math 101 flipped classroom lesson. This is on section 7.2, and in section 7.1 we were talking about roots, also known as radicals. In the definition, we made a connection between them and exponents, and there were a few other hints about perhaps a deeper connection. Well, first we're going to review some things that we should already know about exponents, and then solidify what we know about the relationship between roots and exponents. So first off, when you first learned about exponents, you were probably taught to think about it as repeated multiplication, a shortcut for repeated multiplication. So the exponent would have been some counting number. Well, that allowed us to come up with some exponent rules, and I'm going to try to give some brief explanation in case you have forgotten, or maybe were never told why these rules hold true. So when you multiply things with the same base, we were told to add the exponents. I picked, in this example, two things that are using whole number exponents. And if we think of that repeated multiplication idea, then that would mean we have 3 copies of x times 2 copies of x for a total of 5 copies of x being multiplied together. We can drop those parentheses. But that is the same as if we had just added the 3 plus 2 from those exponents to come up with an exponent of 5 on the x. Now, if we use the same idea of the repeated multiplication in a division question, 3 copies of x divided by 2 copies of x, we could cancel out 2 of them from top and bottom, and we're left with x to the first, or just x. Since an exponent of 1 does not need to be written in the end, we get the same thing if we would subtract from top to bottom the exponents 3 minus 2 to give us x to the first. Notice that since we cannot divide by 0, then x could not equal 0. With x squared over x squared, both copies of x in top and bottom cancel out. So we're left with 1. But on the other hand, if you want to keep going with the fact that when we divide things with the same base, that we could subtract the exponents, if we want to keep that going, then 2 minus 2 will give us an exponent of 0. And so, let's see here, make sure you can see that. Then that must mean that x to the 0 is equal to 1. And since we came up with that with the division, since a cannot be 0 here, then a cannot be 0 here. A, x, whatever we call the base, same idea. All right, so then what if we applied the repeated multiplication idea to this one? 2 copies of x divided by 5 copies of x. You can cancel out 2 other factors of x in the top and the bottom. Whoops, just 2 of them there. It's going to leave us with a 1 in the numerator and 3 copies of x still in the denominator. So 1 over x cubed. But again, if you want to keep going with when you divide things with the same base, that you can subtract the exponents, top minus bottom, then that would give us 2 minus 5 in the exponent, so x is negative 3. So that must be telling us that when we raise a base that is not 0 to a negative power, it would equal 1 over, divide by that base, and change the sign of the exponent. What I'm getting at then is that we don't just have to think of exponents as telling us about repeated multiplication. We could think about them as not only counting numbers, what we were talking about at first there, but we've now allowed for 0, and we've allowed for negative integers. So overall, so far, from things that you would have already known before this class, the rules of exponents can apply to any integer. By integer, I mean something with no fractional or decimal parts. So let me show this. There we go. All right. And in fact, we can go a bit further with some rules of exponents. All right. So again, the previous rules, they were letting us extend from just talking about counting numbers as exponents. So now we can have any integer as an exponent. And let's take a look at 3 more exponent rules. Quick review of those. All right, so this is telling us if we raise something to a power, and then we raise that whole thing to a power that we can multiply. So if I have x cubed squared on the one hand, since that's a counting number or a positive integer, I could have thought of that as x cubed times x cubed and use this to get x to the 6th. but it is quicker to multiply the two exponents. There's no other x in between them. So I multiply those exponents and I get x to the sixth. If we have xy, that quantity getting squared, then I could have written xy times xy, dropped the parentheses, and commuted, moved the multiplication around to get xx, yy, which would be x squared, y squared. For lack of a better word, when we're multiplying and then we raise to a power, for lack of a better word, we're distributing the multiplication. So both of those things got squared there. And last, in the review, if we have the quantity 1/2 getting cubed, on the one hand, we could say, well, let's multiply 1/2 times 1/2 times 1/2, and that would be going straight across the numerator and straight across with the denominators to get 1/8, but that's going to be the same as 1 cubed over 2 cubed. So our answer would be 1/8. So that's saying, just like with the multiplication, for lack of a better word, we could have distributed the 3 across the division to say 1 cubed and 2 cubed and get our answer of 1/8 a lot more quickly. Now, be careful. Those last two only apply for multiplication and division. Okay, so now what we're going to see is that we could have rational numbers like 1/2, 2/3, 3/4, 4/3, 8/5, stuff like that as exponents. What would justify that? So we're claiming that a to the 1/nth power equals the nth root of a, or if you don't have a numerator of 1, that a to the m over n power would equal the nth root of a raised to the nth power, where we have to have that fractional exponent reduced to lowest terms. Why can we do this? Well, think about what we saw in section 7.1, where if we had something like the square root of 5 and we square that, since 5 was already positive, that is giving us a real number, and they're just canceling out to give us an answer of 5. Well, if we did allow an exponent of 1/2, 5 to the 1/2, square that, from what we just saw right here, we can multiply those exponents. 1/2 times 2 is 1, so we get 5 to the first, or just 5. We squared something in each of these. Square root of 5 here, and 5 to the 1/2 here. Both of those got squared, and the answer was 5. So it seems like those are equal, and that is in fact the case. We're using this fact right here. The index on that square root was 2, so 5 to the 1/2 is equal to the square root of 5. Okay, so on these 5 questions, we are asked to evaluate. And since 9 to the 1/2 is the same as the square root of 9, then they are just looking for saying that that is equal to 3. We do not need to use a calculator for one like that because of that connection. This one is talking about the square root of -9, and that's not a real number. Okay, so this one is asking for the 4th root of 625. Because I know 5 squared is 25, and I know that 25 squared is 625, that suggests to me that the answer here is 5. But let's try it out. I will show you doing this on the calculator. Okay, here we go. We're going to need to put in 625 raised to, if you're in the classic mode, put parentheses around that fraction. Otherwise, it would think you have 625 raised to the first power and then dividing by 4. But if you're in the math print mode, it should make it look nicer. 625, when you type this, then 1 divided by 4, no parentheses needed in that case. It understands that that's all up in the exponent. All right, so now 125 to the 1/3 power, that's going to be the cube root of 125. That is also equal to 5. So we change that to cube root 125, and that equals 5 as well. Whereas if we have a negative 125 inside, that's okay, because when we convert that to a radical expression, although that's a negative inside, it's inside of an odd index root. So we have -5 there. So what if in our rational number exponent, we have a numerator that is not 1? Well, because of what we reviewed here, we could write m over n as equal to 1 over n times m, and apply that a to the 1 over n is equal to nth root of a. So a to the m over n is the nth root of a raised to the nth power. Doesn't matter which order we go in. Could we raise a to the nth power first and then take the nth root? Well, in some cases we can, but we do need to be careful because the first part here is the definition. Then if the nth root of a is not a real number, if you have a negative radicand and an even index, then this would not be real. And so it would not make sense to continue by raising to the nth power. That can get hidden by using this other approach. And one other thing, the n being in the denominator, I think of that as underground in the fraction. So that's showing up as the index of the root. The root of the fraction is going underground as the index of the root. So when we have 9 to the 5/2 power, I actually like to apply the first one because that can let us deal with some smaller numbers. That's talking about the square root of 9 raised to the 5th power, rather than figuring out 9 to the 5th and trying to take the square root of that. Take the square root of 9 first, raise that to the 5th power, and it should give us 243. If I check on the calculator, first of all, I'll just type it in directly. 9 to the 5/2 power, that's giving me 243. But if I had not used the calculator, what if I'd raised 9 to the 5th power first, and then tried to figure out the square root of the previous answer? I would not have known that 59,049 was a perfect square and that its square root is 243. As for this next one, that's asking for the square root of -9, then cube it. Yeah, there we go. So square root of -9 is not a real number, then -9 to the 3/2 is not a real number. In those two examples, we had improper fractions, whereas on these next two, we've got proper fractions. Doesn't matter. The rule works the same way. So what we're looking for here is to take the cube root of 125 first, and then square that whole thing. The cube root of 125, so without even using a calculator, knowing the cube root of 125 by heart is 5. I'm going to have 5 squared, and that's 25. If I check that on the calculator, 125 to the 2/3 power. Again, I'm in the classic, I'm in the math print mode. So if I was in classic mode, I would need parentheses around the fractional exponent. And as for the other, well, that would be the cube root of -125, and then squaring it. We would have the cube root of -125, and then square that. Well, that is a negative radicand, but the index is odd, so that's okay. Cube root of -125 is -5. When we square the -5, we also get +25, just like the previous question. Now, what if we have a fractional exponent, but it's negative? We know that a negative exponent would tell us to put something down in the denominator. So this would equal 1/9 to the 5/2. That's something we already did, because that would be telling us to take the square root of 9, which is 3, and then 3 to the 5th is 243. On this one, it'd be telling us to put this down in the denominator. -9 is now to the +3/2. Well, that's telling us to take the square root of -9 and then raise it to the 3rd power, put that underneath a 1 in a denominator. But we can't take the square root of -9, so that's not a real number. Now on this one, we could blindly follow the previous stuff, and then this would be telling us to take the cube root of 8/25 and then square it. This is actually not going to be the nice way to answer the question, but here we go. So we would have the cube root of 8/125 cube roots. And then we're going to square that. And there it showed up nicely. Okay, well, that's going to give us the cube root of 8/125, because we know the cube root of 8 and we know the cube root of 125. That's going to be 2/5. Then we're going to square that. Based on this rule, that's going to give us 4/25, but we don't like fractions inside fractions. So that's like 1 divided by 4/25. Some of you might refer to this as copy dot flip, 1 times 25/4 for a final answer of 25/4. I think it's nicer when you see a negative exponent applied to a fraction to flip the fraction, change the sign of the exponent, and then we would have the cube root of 125/8 getting squared. So 125/8 due to switching the sign of the exponent to positive. Okay, so that's going to give us Inside 5 over 2, now square those. 25/4 a lot more quickly. All right, here we have one with a variable, and I'm going to show my work and then the final answer, then erase the work. We've got q raised to the -10/7. I'm going to show my work. First, moving that to the denominator, changing the sign of the exponent, and then they want us to express that as a radical. So they also say use the definition that takes the root first. We'll have the 7th root of q, and then that whole thing is going to be raised to the 10th power. So now erasing that work, checking the answer, and it's good. On the next one, we have all of 2y plus x. All of that is being raised to the 2/3 power. So the denominator being 3, the root goes underground. So that's going to be cube root of all of 2y plus x. And then that whole thing, we're going to raise that to the 2nd power. And that's good. Here we have 7 to the 8th. We're taking the 4th root of that. So that means with a fractional exponent, that would be 7 to the 8/4, which is reducing to 7 squared, or 49. Erasing the work, checking the answer, and it's good. Okay, we've got the square root of x to the 12th. Remember, although the index is not written, the index of a square root is 2, and so that's x to the 6th. And they tell us to assume that all variables represent positive real numbers, even if they hadn't told us that, because the power after we reduced is even, this would come out positive anyway. Here we're to multiply two things with the same base. So we add the exponents. Luckily, they have the same denominator. So 4/5 plus 6/5. That's going to be 2 to the 10/5. That reduces, so 2 squared, and that's going to equal 4. Dividing things with the same base. We subtract the top exponent minus the bottom exponent. So we'll have the base of 9 raised to whatever 9/4 minus 7/4 is, and that would be 9 to the 2/4. That reduces to 9 to the 1/2, and that represents the square root of 9. So overall, we should have an answer of 3. Now they may just want us to leave it as 9 to the 1/2. Let's find out. Okay, they're happy with that. Here we're back to multiplication, but we have different denominators. Add those exponents, 11 over 16 plus -1/2, but then get a common denominator of 16, and adding a negative would be the same as subtracting. I'll multiply in the 1/2, top and bottom, by 8. So 11 minus 8 is 3. That's all over 16. And although we could convert that to the 16th root of a cubed, they're telling us to write our answers with exponents. Notice that it says positive exponents. So let's check a to the 3/16. This one gets a little more interesting. But if we convert y to the 11th 12th root of that, it's y to the 11/12 times y to the 1/3. Get a common denominator again and add the exponents. Multiply in the 1/3, top and bottom, by 4. We'll have 11/12 plus 4/12 in the exponents, which would give us 15/12. 3 goes into both of those, so y to the 5/4. Right, radicals as exponentials. Give the final answer in exponential form. Okay, so it should be y to the 5/4. And here's our last one. Meteorologists can determine the duration of a storm by using the function t of d equals 0.07 times d to the 3/2, where d is the diameter of the storm and t is the time in hours. If we have a diameter of 9, then this is saying take 0.07 times the square root of 9, then cube all that. So 0.07 times 3 cubed, which is 27. (1.89) but they want us to round to the nearest tenth of an hour. So 1.89 will simplify to 1.9. Notice I was following the order of operations there. Okay, that's all that I have on this one for now. Hope it helps, and I'll see you in class.